From reimagining propulsion systems with innovations like variable thrust and reusable engines to pioneering methane-based fuel technologies, NASA has boosted rocket efficiency. These advances promise more cost-effective and sustainable space missions, expanding our reach to Mars and beyond. But how might these innovations shape the future of space exploration? The Space Shuttle Main Engine, SSME, also known as the RS-25, initially took shape in the 1960s and began intensive development in the 1970s. The engine's maiden flight occurred on April 12, 1981 during the STS-1 mission, marking a significant milestone due to the completion of extensive development work. The engine had a number of upgrades to boost reliability, safety, and maintenance effectiveness over its operational life. During the Space Shuttle program, the orbiter was powered by 3 propulsion units. These engines used fuel from an external tank to generate propulsion throughout the spacecraft's ascent. After the flight, the RS-25 engines were thoroughly inspected and disassembled. Components were cleaned, evaluated for wear or damage, refurbished or replaced as needed, and then reassembled for future missions. This process ensured each engine met the stringent standards for required spaceflight. The RS-25 engines are integral to NASA's Space Launch System, SLS, powering each core stage with a collective thrust exceeding 200 million pounds during launch. These engines have been modernized and refurbished for SLS missions. RS-25 engines offer unparalleled flexibility, capable of throttling between 65 and 109%, enhancing control throughout different stages of flight. Moreover, intense safety measures, including redundant systems and advanced sensors, ensure operational reliability by swiftly identifying and addressing issues. Before being integrated into the SLS, every component must pass thorough ground testing to ensure that it meets safety and performance requirements. This demonstrates the engine's ongoing engineering quality and adaptability for further space exploration projects. NASA is expanding its engine technology by developing the Rotating Detonation Rocket Engine, RDRE. This unique device, which was recently tested successfully at NASA's Marshall Space Flight Center, uses a revolving detonation mechanism to consume fuel, producing over 5,800 pounds of thrust for more than 4 minutes. NASA's next-generation rocket, the Space Launch System, SLS, incorporates numerous engine technologies to ensure efficient spaceflight. During liftoffs, it uses 4 RS-25 engines and 2 solid rocket boosters. These engines, originally designed for the Space Shuttle, play an important part in forcing the rocket into orbit and contribute greatly to its overall performance. NASA is working on improving fuel economy in aviation through various technologies. The N+2 airframe, incorporating advanced materials, aerodynamic designs, and structural innovations, is expected to reduce fuel consumption by 31% due to enhanced aerodynamic efficiency, weight reduction, and drag reduction. NASA is also exploring innovations in propulsion engine technology, including advanced turbofan and open rotor engines, and hybrid electric propulsion engines. These engines aim to optimize the thermodynamic cycle, improving component efficiency and reducing specific fuel consumption. Optimizing jet engine designs by decreasing the core size improves bypass ratios. A higher bypass ratio increases efficiency by producing greater thrust with the same fuel consumption rate, further enhancing overall fuel economy. The Revolving Detonation Rocket Engine, RDRE, is an innovative propulsion technology that uses a revolving detonation combustion process. Unlike classical rocket engines, which use constant state combustion, the RDRE uses supersonic shock waves to ignite fuel and create thrust. This approach has various advantages, including increased efficiency and the ability to develop lightweight propulsion systems. Engineers at NASA's Marshall Space Flight Center in Huntsville, Alabama, recently successfully tested a 3D printed RDE for an astonishing 251 seconds. This performance satisfies the strict standards for crucial operations such as lander landings and deep space burns, which are required for missions to the Moon and Mars. It is made of sophisticated materials, including the copper alloy GrCop42. These substances allow the engine to operate in severe temperatures without fear of overheating, so the researchers are currently attempting to scale this technology for higher performance applications, investigating its applicability for various mission types including landers, upper stage engines, and supersonic retro propulsion systems for Mars landings. Thomas Teasley, a NASA combustion devices engineer, emphasizes that the RDE offers a considerable improvement in design efficiency, with the development of lightweight propulsion systems potentially driving heavier payloads farther into space, aligning with NASA's ambitious Moon-to-Mars exploration goals. In order to withstand the powerful explosions that occur during operation, the injectors and other engine parts need to have exact forms. These complex shapes could not have been created without the support of 3D printing technology. Complex portions that would be difficult or impossible to construct using traditional procedures may now be made because of this technology. For instance, the employment of fuel diodes to manage backflow in injectors ensures smooth and controlled fuel delivery. In addition, several engines have nozzles named aerospike nozzles, which increase efficiency at different elevations. Unlike conventional bell nozzles, adjust to variations in ambient air pressure to maintain optimal performance while the rocket raises the atmosphere. Due to their enhanced adaptability, the engines function more effectively under a variety of atmospheric conditions. The advanced propulsion system utilizes cryogenic liquid hydrogen and liquid oxygen to achieve remarkable performance metrics. It provides a vacuum thrust of 512,300 pounds of force equivalent to 2.279 millinewtons and a sea-level thrust of 418,000 pounds of force totaling 1.86 millinewtons. Its specific impulse reaches 452 seconds in a vacuum and 366 seconds at sea level, demonstrating high efficiency. The engine can operate within an impressive temperature range of -253 to 3,300 degrees Celsius, which is equivalent to -400 to 6,000 degrees Fahrenheit. The design incorporates a full-flow staged combustion cycle where both fuels are completely burnt in separate pre-burners before entering the main combustion chamber, showcasing advanced aerospace engineering capabilities. The turbopumps, which provide the pressure required to deliver propellants into the combustion chamber, resulting in excellent efficiency and performance. To control the severe temperatures during the operation, the RS-25 employs regenerative cooling, which involves flowing through channels in the nozzle and combustion chamber walls, absorbing heat and preventing overheating. Thrust Vector Control TVC allows for precision steering during ascent and orbital maneuvers by gimbaling the nozzle. The engine is built using modern materials, including a carbon composite nozzle extension, and is designed to withstand many firings and refurbishments. The RS-25's ability to regulate its thrust over a wide range is critical for precision control during various flight stages, allowing for flexibility and adaptation to changing mission requirements. In future, NASA will continue to enhance and expand the use of reusable rocket engines. Engines like SpaceX's Merlin can significantly lower launch costs by enabling multiple flights with minimal refurbishment. Research into advanced propulsion technologies, including ion drives and nuclear thermal propulsion, is expected to produce breakthroughs. These systems offer higher efficiency and faster travel times for deep space missions. Future generations, such as the RS-25E now in development, attempt to simplify designs while preserving strong performance. With over 3,000 successful starts and more than 1 million seconds of combined ground and flight testing. Additionally, NASA is also actively investigating eco-friendly propellants. Alternatives like methane-based fuels could replace traditional chemical propellants because it is more stable than hydrogen, decreasing pollution and improving safety. As commercial space companies expand, collaboration between NASA and private entities will increase, with joint efforts in engine development, testing, and deployment shaping the future of space exploration. With the Artemis program and Mars missions on the horizon, NASA will invest in powerful engines capable of supporting crewed missions to these destinations. These engines need to be reliable, efficient, and adaptable to various environments. A series of hot fire certification tests is underway at NASA's Stennis Space Center for a redesigned RS-25 engine that will support the future SLS flights after the current inventory is depleted. As we wrap up, it becomes clear that the relentless pursuit of innovation has not only transformed the capabilities of space exploration, but also set new benchmarks for efficiency, reliability, and sustainability in propulsion technology. What challenges do you think NASA might tackle next to further advance rocket engine technology? Share your thoughts in the comments and don't forget to like and subscribe.